There we go. All right. Well, back in the 90s, I wrote some papers about how isolated quantum systems, oops, not high enough. Thank you. Back in the 90s, I wrote some papers about how isolated quantum systems in pure states can come to thermal equilibrium. And some of the ideas in those papers have occasionally found themselves into papers about black holes, most recently Joe and Don's paper. And so I was asked to briefly explain those ideas, which is what I will do. I should mention that at the time, actually somewhat before my papers, Josh Deutsch at Santa Cruz wrote a very similar paper. And there's also been a modern resurgence of interest in this subject, which has been triggered by experiments in atomic physics. Atomic physicists can do things like take clouds of cold atoms in a laser trap and collide them and follow what happens. And sometimes these clouds seem to thermalize, and sometimes they don't. And there's been a lot of interest in understanding exactly how this all works. And in particular, in 2007, there was a paper by Marcus Riegel, Vanja Junko, and Maxime Olshani, who were all at Caltech at the time, on some of these experiments, and which referenced some of Josh's and my ideas. And so this is all taken off. There have been several workshops here at the ITP about this, I'm mentioning all this because the evidence that what I'm going to tell you actually works in real systems is now much stronger than it was at the time we were writing our papers. So what is the basic idea? I'm going to assume we have some quantum system with many degrees of freedom in it, but a finite number of degrees of freedom and in a finite volume. And so we'll have, so for example, a box of gas, a lattice field theory or spin system, anything like that would be in the category of things we're going to consider. And so it has some Hamiltonian, and the Hamiltonian has energy eigenstates and energy eigenvalues. And because it's got a finite number of degrees of freedom in a finite volume, the energy eigenvalues are discrete. And we assume that the system is isolated. So that means we can write down its instantaneous quantum state as an expansion in energy eigenstates with just simple phases. So I'm going to make a couple of mild assumptions about this state. One is that it has an energy. Maybe we'll write this like this. Which scales like the number of degrees of freedom. And what I mean by that really is that we have some finite, that is non-zero amount of energy per degree of freedom. We're significantly above the ground state. And I will also assume that the quantum uncertainty in the energy is small, that it's much less than the total energy. And I've discovered in giving talks, many people like to be specific. So if you want to be specific, we'll say it scales like some inverse power of n compared to the energy. I remind you that if we took as our state a mixed state that was a thermal density matrix, we would have an energy uncertainty that went like n to the minus 1/2 times the total energy. Okay, and now I'm going to assume we have a set of observables, and I'll pick one of them that I'll call A. We could put an index on A to tell us which one, but I'll just call it A. And we're to imagine that this A and its friends are things you could actually measure in some sort of real experiment or caricature of a real experiment, and that there's a finite number of these, and not a whole lot, certainly no more than a power of n. So we certainly don't have an exponentially large in n number of these. And of course, in the real world, you have, maybe 10. You don't have a great deal. But anyway, so we'll focus on one. And I want to focus on the time dependence of its expectation value. So this just means the expectation value in the state. And we assume not only can we observe this thing, we can also prepare states with a specified expectation value. So at time 0, we've given this observable some expectation value, which is far from equilibrium. And because we all took the class in statistical mechanics, or because we all live in the real world, we expect that if we follow what happens to this expectation value, it will do something like this. It will move to some other value, which we will identify as the value in thermal equilibrium, and then it will stay there most of the time. Maybe there'll be some fluctuations, but most of the time it's going to stick to this value. Okay. And I guess to be precise, down what I mean by athermal. I just mean the usual canonical expectation value where beta is fixed by saying that the thermal expectation value of the energy should be equal to the actual quantum energy. And so I've already basically alluded to this, but we really need a definition of thermal equilibrium. And so I will use the following definition. We'll say that the system is in thermal equilibrium. Put quotes around it to emphasize that it's my definition at time t if the difference between the quantum time-dependent expectation value and the thermal expectation value is less than some number epsilon, which we should think of as some sort of experimental tolerance when we make our measurements. Yeah? Well, okay, so I am caricaturing the measurement process by saying we're going to look at quantum expectation values. In the real world, it's very hard to actually look at an expectation value. If we want to study fluctuations of A, then we should put A squared on the list of observables and look at the expectation value of A squared. So that's how I'm going to deal with fluctuations. Yeah, you can demand that. I think if you actually told an experimentalist you want him to, to make the measurement to 10 to the minus 12 accuracy, you might get thrown out of the lab. But we're all theorists here, so you can do that.
So you have in mind that this should be true for a whole list of?
Yes. Sorry, I didn't. No, for a set of it. So we make a list of the observables that we are going to measure. Okay.
Do you have an idea of what the maximal scaling within of the size of that list is? So
I would say a power of n.
a power of it.
Certainly not exponential with n.
Yeah, obviously.
But I think it would work. Certainly, if you had some sort of lattice field theory or spin system, you could put all local observables on the list and maybe all bilocal observables on the list, for example. Okay, and so now I want to ask the following question. Can we get thermal equilibrium at most, and if it matters, then we can be a little more precise about what most means, but can we get thermal equilibrium at most times T for all state psi that meet the conditions above? That is, I consider all states that have a given expectation value of energy and have a quantum energy uncertainty that's less than some maximum value. And I now want to ask, is it possible for the quantum expectation value to match to within some tolerance the thermal expectation value at most times, as it does in the picture, without placing any further restrictions at all on the state? And the answer is yes. If
Is an energy eigenstate found in all?
yes, that's the most important point. Let me introduce some notation. I'm going to write Greek subscripts on A mean matrix elements of A in the energy basis.
There must be some restrictions on what they are. Surely there are some operators that won't do this.
Yes. All right. So far, I haven't been at all specific about the kind of system we have, except to say it's got lots of degrees of freedom. And we will want the observables to be things that you could actually imagine measuring. So I will not allow you to write down an operator by just specifying its matrix elements in the energy basis. And I'm about to get more specific about the kinds of systems that we know can satisfy them. Okay, so what does this say? All right, and I'm skipping the math that leads to this, which is really quite simple. It's in my old papers. Well, I'll give a reference at the end if anyone wants to read a paper, but the math is very simple, and it leads you to this conclusion that these diagonal matrix elements, each diagonal matrix element in an energy eigenstate of this observable has to match the thermal expectation value at the same energy. And the off-diagonal matrix elements have to all be small. So this is some simple math that you could all do. You could conclude that if this is true, then the answer to the question is yes. So now the question is this in any way a reasonable thing to expect? Can we identify a class of systems for which this is true? Let me just emphasize that what I like about this is that it's now translated a kind of murky issue of what it means for a system to be in thermal equilibrium to a question that's just a quantum dynamical question. If you had a system and a list of observables and an infinitely good computer, you could just compute this and see whether it's true or not.
Yeah, I'm really confused about these words. It sounds to me, reminded the second episode about the calculator, this is much smaller than the first one, which is probably rather than less. Doesn't the second one have to be exponentially small? I mean, to ensure not only a and a squared
I'm about to tell you that in the class of systems I want to consider, it is exponentially small, but it doesn't have to be. I mean, if you just...
If one is d squared also thermalizes, then it's probably that.
I think that's not quite right, because I think you will still be able to have some large ones, and I think they won't all have to. You can have some. If you think of epsilon as kind of big, like power of n, inverse power of n, as opposed to exponentially small, you can get away with most of them being 0 and some of them being large. But this is a minor technical point. If any of these things is violated, you can find a state which will not be in thermal equilibrium at most times. Okay. Now, traditional presentations of StatMech talk about typical states and most states. And all right, so what I like about this is here I'm making another thing I like about this is that here I'm making a statement about all states, and so I don't have to worry about what most means or what typical means. Sorry? All right. So what do you actually need to derive this? If you take the infinite time average of A of t, and you assume the states are non-degenerate, you get this. And so obviously the infinite time average has to be close to the thermal average. And so, but I get to weight these diagonal matrix elements with my coefficients for my state, which I got to choose. So if I'm allowed to weight these arbitrarily, it had better be that each one of these matches the thermal state. And the other thing you can take, let me call this A bar. I can take A of t minus A bar, square that, and time average that. So over bar means time average. And this will come out to be okay. And I'm going to say that if the fluctuations of this expectation value about it, the fluctuations in time of this expectation value about its mean value are bounded, then that's what I mean by most of the time. Because if this is less than epsilon squared, that means that when I integrate the squares of these fluctuations, I have to, so at any particular time, I would be allowed to go above, but I couldn't do it for very long, and that would have to be balanced by going below. So that's what I mean by at most times. And that's where these things come from. So I now did the math that I said you could do yourself.
In that first inequality, what's the definition of the second term?
All right. Where are we?
On the board, you have the two inequalities, the answer to your yes.
Uh-huh.
What's the definition of A subthermal of PCL?
A subthermal is defined up here. It's just the canonical thermal average at a temperature which is fixed by saying that the energy is some value. So now the energy we're using is the energy eigenvalue. Okay, so, all right, so the punchline now is, so now we can ask another question, question 2, is there a class of systems for which this is true? And, of course, the answer is yes. If you take a classically chaotic system and quantize it, you can, at varying levels of rigor, prove these things. So there's a quite rigorous statement that says that the diagonal matrix elements at very high energies approach the classical microcanonical average, which is actually a little bit stronger than what we need here. More weakly, you can say that the diagonal matrix elements are small, and the off-diagonal matrix elements are small, and they are, as mentioned, in fact, expected to be exponentially small. So, in a quantized chaotic system, these matrix elements take the following form. All right, so I've defined a bunch of things here. So script A is a smooth function of the energy, which is essentially equal to the thermal expectation value. So if I draw a picture of A alpha alpha versus E alpha, this is a discrete set of points, but they're supposed to lie on a smooth curve. Well, I can't draw my smooth curve on top of the points, but the smooth curve is this function script A, and the points are supposed to lie on top of some smooth curve. And then, if you take a thermal average, you'll be weighting these with Boltzmann weights. The way I've drawn it, Boltzmann weights don't look like they're giving a narrow in energy average, but actually they are because of the way the density of states works and so on. So Boltzmann weights are just one particular weighting that will pick out an energy window. How many n's in Boltzmann? That goes like n to the minus 1/2. But then we also can weight with these C alphas. Right, so the C alpha squareds look like that. But again, it doesn't matter that these fluctuate a lot, because as long as they're within a sufficiently narrow energy window, which we've assumed, it doesn't matter how we weight, because these are all essentially the same. So we get the same answer. And again, in quantum chaos, this smoothness is called Schnirelmann's theorem. It also follows from Michael Berry's random wave conjecture about the nature of energy eigenstates in chaotic systems. It also follows from an analogy between quantized chaotic systems and random matrix theory that makes a lot of predictions that turn out to be true. The other aspect is that the off-diagonal matrix elements here, and also there can be exponentially small fluctuations in the diagonal matrix elements. These are exponentially small. S here is the thermodynamic entropy at energy E, which scales like n. And this part comes very simply just from saying that if we took an expectation value of A squared, we could write that by inserting a complete set of states as a sum over beta of alpha beta squared. If this is some reasonable observable, then A squared should be a reasonable observable, and its diagonal matrix element should not be exponentially large. On the other hand, we're summing over an exponentially large number of states over here. but we're not getting an exponentially large answer. How can that be? Well, there are two ways. One is most of these are 0. That's what happens in integrable systems. There are selection rules, and most of these matrix elements are 0. Or they could all just be very small. And that's what happens in chaotic systems. They're all just very small. Okay. So here we have a picture of how isolated quantum many-body systems can come to thermal equilibrium. We have a sort of practical definition of what we mean by thermal equilibrium. We have to identify a set of observables. And then we just ask that their quantum time-dependent expectation values be equal to the thermal expectation value to within some tolerance. Then we ask that that be true of all states that have a reasonably well-defined energy. And then we find out that that can be true if the matrix elements satisfy certain properties, and that we know a class of systems where, to a very high degree of confidence, we believe that those matrix elements will satisfy them. Okay. So, and I guess I didn't say here, in the quantized chaotic system, A can be any observable that has a nice classical limit. You're not allowed to use H bar when you write down your A. Tom.
Mark, I believe when one talks about this in terms of what the Hamiltonian is, you're effectively assuming the Hamiltonian is picked from the Gaussian random ensemble or something?
Well, so quantized chaotic systems have properties that are many properties in common with Hamiltonians picked from the Gaussian random ensemble.
So what I wanted to ask was, people have been discussing different versions of chaos, scrambling, and so on, which are not as violent as a random Hamiltonian. And do you know how much of this transfers over if I make some assumption like that?
Well, there are a lot of different sets of questions people ask. I mean, there's some interesting work in the quantum information community of asking how hard is it to diagonalize a Hamiltonian and relating that to this kind of behavior.
So it's not, you don't need the sort of generic random matrix in order.
No, and I think it's wrong to think of a particular system as being drawn from a random matrix ensemble. When Hubbard wrote down the Hubbard model, he didn't go to a drawer labeled Haar measure and pull something out. He wrote down a specific thing. So in physics, we're writing down specific things. And then the question is, does a specific thing that we have happened to write down for some reason have properties in common with something drawn from a random matrix ensemble? And there are cases where this is a useful analogy, and quantized chaotic systems are one of them. What? Well, n equals 4 super Yang Mills seems very, it's got all kinds of conserved quantities. Yeah. I do not know. I wish I knew.
Mark, is there anything that you can say about how close the density matrix of small subsystems come to thermal as a function of the size?
Yeah, it's exponentially close. That's basically what this all implies.
But of course, as the subsystems get bigger and bigger, eventually they're in the whole system.
Right.
So can you see anything like page behavior or?
Well, I haven't really. All right, so that's now. I'll rephrase that by saying you're enlarging your set of observables. You start with, say, one body, then two body, and you keep going and going. And among atomic physicists and people who are working on this, nobody thinks about that because that's your experimental friends are not going to do that. So I don't know. I would strongly suspect that it's very similar to page type behavior, and so that it would.
Even for the pure state.
Yeah. But I mean, Don,
For the energy eigenstate.
yes. That's what I would expect.
I just wanted to make a connection to this question. Any proof for finite anomalous certainly does obey this hypothesis. It does have these operators that have this kind of behavior. I mean, just to say this is, maybe this is not exactly the way you would say it, but this is not a very strong assumption. It's simply the assumption that the energy eigenstates don't care too much about what operator you're getting. So, the operator just has random matrix elements between energy eigenstates. And I mean, this drops out. I don't know. This is quite a way.
No,
Energy eigenstates don't care about which operator you're using.
So, I mean, the modern work that's been done in recent years is really concentrated on trying to figure out where this sort of behavior sets in. So certainly if you have an integrable system, it's not true. Okay. And now you turn on small non-integral perturbations. It turns out it's still not true. You need to crank up the perturbation to make it strong. And so I think that's not surprising from one point of view. Another point of view is you might have thought, a very weak perturbation would be enough in a many-body system. That many-body would help, but it doesn't. It still needs to be a strong perturbation.
Very small. That's an argument that small 1 over n functions are enough.
Yeah, 1 over n is not enough. Yeah. Well,
It's also enough.
It's supposed to be integrable, right? When it's finite and you don't think that it's in the close. There's some question.
well, I am not the person to ask large n Yang-Mills question to, but.
Anyway, even if you turn on a very weak perturbation in a very many-body system, wouldn't you expect that all degeneracies would be lifted and you have exponentially small spaces between energy levels?
You expect degeneracies to be lifted, but another diagnostic you can use is the energy eigenvalue spacing distribution, which for a random matrix is Wigner-Dyson. And for an integrable system is Poisson. And so if you take an integrable system and you turn on a small coupling and ask what happens to the spacing distribution, it does not change right away. You have to crank that perturbation up to order 1 in some specific units before the spacing distribution changes.
Can you give us an example of this statement? What system, what's the system, and what are the values?
Oh, well, some sort of Hubbard model-like system. So you take some system with hopping and like on-site repulse, so hardcore bosons is a system people like. And then you turn on, and you can, so at the simple, this can be integrable, and so, and then you turn on a next to nearest neighbor hopping, and you have to crank that up so its coefficient is large, order 1 compared to the coefficients of the other term. That's in 1 dimension. But dimensionality shouldn't matter for this. It's the same. It's the same in classical mechanics. If you can take a classical many-body system, and if it has integrable behavior and you add a small perturbation, it remains integrable. You distort the KAM tori, but you don't destroy them, right? So this is the quantum analog.
Mark, you wouldn't claim that a small perturbation of a generic free field theory doesn't make the system chaotic, right?
Does not? Yes, I would claim that.
Really? So yeah. I don't
This is Fermi Pasta Ulam from 19.
No, quantum field theory.
Yeah, QED. Yeah.
Well.
The thing is that there was questions on the last one, that having an evolves instead of the tora, the distribution of high energy is a quantum distribution. The pit is called very active pit, and then due to scattering it will go like that.
No. That's a different question.
There's order 1 is n plus 4, right? So if you make n very large with finite, but then you look at states whose energy is order n squared, and you think it's thermal, but then you look at states whose energy is order 1, you don't
I have nothing in particular to say about n equals 4 Yang mills or even.
What about just three particles and then a small repulsive interaction? Three particles and not more than three.
That's a good question, and the most naive answer is that you really need the wavelengths of the particle to be small enough. Oh, classical.
Doesn't it go chaotic immediately?
If you turn on a small radius hard sphere, it goes chaotic immediately.
So isn't that a capital example of 57? Well, I guess
Well, you have to be careful. It's definitely true that if you turn on a hard sphere, but if you turn on a repulsive potential, then that's not going to be true at sufficiently low energies. It stays integrable, yeah. What happens as you go to very high energies, I'm not sure.
Does that also mean that it doesn't thermalize?
Yeah. So there are plenty of, another class of systems that's now being heavily discussed by condensed matter people is systems that exhibit many-body localization, which means that the energy eigenstates do not spread out over phase space, if you like, which is essentially what's happening here. Some people argue that this can persist at arbitrarily high energies, and so there's a raging debate in the condensed matter community about it. Oh, yes, sorry.
You said sufficiently low energies.
Yeah.
Now, do you mean sufficiently low energy densities or sufficiently low energies?
Yeah, that's a good question. It may be that the energy, scales not like n, but like n to the 1/2 or something like that.
I don't like to.
Yeah, n to something.
Just another version of my question showed that this is a sufficient condition, but necessary.
Well, okay. So if you certainly, all right, so certainly this is stronger than this, right? So I have really small off-diagonal matrix elements here. So certainly you can relax this. The problem is that if you tend to relax this, these guys start unrelaxing as well. And then there's a big, over in atomic physics land, there's a big debate over if this is not true, then it's not true that all states will come to thermal equilibrium, but a subset of them still will. So what is that subset, and is that good enough to have that subset come to thermal equilibrium?
Okay, let's meet back at 11:45 so we can hear Alexei.